Okay, this is the third lecture on the Introduction to Axiomatic Design. And in this lecture, we're going to be talking about Axiom 1 and getting started with design matrices and prioritization. So the way we're going to apply Axiom 1 now in a formal sense is using a design matrix. Axiom 1 can be used sort of informally or qualitatively in lots of ways. You can just look at a problem and say, geez, you know what, I think we're sort of coupling some things here that don't need to be coupled. Let's see if we can sort it out. And before we had Aclaro software, that was a lot of the way that it was used. Aclaro now allows us to take a much larger decomposition and take a look at the coupling in it. Actually, we've done this on several on designs with several thousand FR-DP pairs. So Aclaro's quite useful in that way, and it's actually I find it's for me it's biggest sort of advantage, its strongest point. So we're going to look at coupling, decoupling, and avoiding imaginary complexity. So in the second lecture, we talked about DPs, design parameters, and how they're used to satisfy the FRs. So here's the question that you should be asking yourself. What is the best order to adjust the DPs to get the FRs that you want? Now, if this is a processing problem, what order do I do processes in? If we're, say, designing a design process, then we're looking at what order do I do the design in? Because if one component or system is depending on the output of another one, I may have to design that first system before I know what I'm doing in the second one, or at least some elements. The design matrix will help you see what those are and avoid those kind of situations. So we're going to see how to assess designs using Axiom 1. What is the best order of adjustment? So one of the things we would like to avoid in a lean kind of design procedure is non-value-added iterations. And so we'll see. And as I said, which components should be designed first. All right, let's take a look at a problem from Sue's 1990 book, Principles of Design. And in this case, what we have is this is a reaction injection molding. So we have two reservoirs, all right, and the components of those two reservoirs is going to mix and get injected into a mold. And the original design that went to MIT, and actually when I was a graduate student, I went by and while they were working on this or a similar project. So this is a case study that Sue developed in this book. So there's two high-pressure pumps that take these two reactants, two components that will then mix in a mixing head and get injected into a mold and then form some sort of polymer part called reaction injection molding, because it starts reacting here once they get together. So the original design had really three FRs. So first of all, we're trying to deliver three different things, and one is related to a high flow rate, another is related to mixture, and another is metering. All right, so high flow rate is because this stuff starts to react and you've got cycle times you'd like to meet. The adequately mixed is because if these are two components that need to react, if they're not mixed well enough, you've got poor quality control. You've got some part that's sort of sticky because it didn't get enough of one component and it didn't completely react. And then metering, if you don't get the right proportions of the two, you need something close to a stoichiometric mixture of these components in order for that to work. So the interesting thing here, and the thing that you want to keep in mind as you're doing designs, is that we actually can assign variables to these three FRs. These are the things that we need to be able to measure to see if they're going to work out. Now, the customer need here is for a good part, another is for a cheaply made part or inexpensively made part. So you can see how these FRs come from that. And you can put tolerances on those FRs. So there are functional tolerances that go on the FRs. We've spoken about those in the earlier two lectures. So what are the DPs? Well, if you go back and take a look at this system, we really have got the high pressure pump and the mixing head. And so we have the pump speed that we can adjust, and we have the nozzle size in the mixing head. So we've got 3 FRs and 2 DPs. So we can write a design equation as we're working on this matrix. And so here are the 3 FRs. And what we're dealing with is change. Right? So this is one of the things that Newton discovered. Change is important. Rather be working with folding money, but we'll work with change. All right, so these we're looking at, so what happens, how do we change the FRs or adjust the FRs by adjusting the DPs? So that's why we have a D in front of all these things. We're looking at how they change. And the thing that relates them to each other is this A matrix. So the A matrix tells us how we get from these DPs to these FRs. Now, we already assigned some variables to those, so we can substitute them in. So what does A look like? Well, A looks like a matrix full of partial derivatives. And so very simply, what we're looking at is a series of equations. And so this is telling me how the Q is the flow rate. How does that change with W, the pump speed? And this one tells me how does the flow rate change with the head diameter. Now, what we're going to do for a lot of our work is transform this matrix into this one. And the X's are going to mean there's a non-zero value, and the zeros, the O's, are going to mean there's a zero value. So what we're saying here is that this quantity, the partial of the flow rate with respect to the diameter of the head is 0. It's not changing. And then in this case, though, the flow rate does change with respect to the pump speed. Now, you might say, geez, if I make the diameter of the head small enough, nothing's coming out of it. So how could that be 0? And the thing is, if we look through the diameters of the head that we're likely to be using, it's not going to have what we would consider to be a significant impact. In other words, the head diameter is not going to take the flow rate out of the tolerance. However, the pump speed would. So this one gets a non-zero value, and this one gets a 0 value. And we'll see more details on this. So we could continue and say, all right, how does the mixing change with the head speed, and how does the metering change with the head speed? And so we're assigning non-zero values to those, which so makes some sense from sort of the physics of the situation, and we can go into more detail on that later. And, oh, good, yep. So maybe I should get rid of all of my marks here, and so we can see. So this is essentially what I've explained. I guess I should know my slides better. There we go. All right. And so there's the 0. Okay, so there it is written out. Here's another element of the matrix. So this is saying that the mixing is influenced by the pump speed. So that's what we were just talking about. All right, so what does, so here's another way of, with the X's and the O's, looking at this matrix. And so a lot of what we're going to be doing is just X's and O's. And what we're looking at, essentially, is going down these columns, going down the columns of the DPs, saying, does this DP influence that FR? And we looked at that a little bit the first time. Now, here is the issue that comes up. We've got 2 DPs and 3 FRs, similar to the Virginia and the Monitor kind of problem that we were looking at. So we can't independently satisfy 3 FRs with only 2 DPs. So, and here it is written up. So while FR1 can be satisfied by DP1, we change DP1 and that's going to influence FR2 and FR3. I've only got one other DP, so I can either get FR2 where I want it or FR3 where I want it, and in general I can't do both of them, because once I change DP2 to get FR2 where I want it, FR3 may be out of tolerance. I get it back in tolerance again. Now FR2 is out of tolerance, so then I change DP2 again, and so forth. So I might get into a never-ending iteration on that. So that's not a good design. So the influence goes down the columns, DPs to FRs. So, all right, so what we need to do is either redefine the FRs or add another DP. And here's what the new machine was. And so they've added another DP. So instead of, so there are now two pumps, right? A high pressure pump on both sides and a precision pump. And there's a mechanical shaft connecting these two. So this could be a kind of gear pump or metered pump that is going to be driven in such a way that it can get the right proportions. So if we just take a look at this intuitively, the high pressure pump is going to ensure that we have the flow rate that we need. So that's going to get the pressure up, and we'll have a big pressure differential across this pump. So the pressure here is going to be low coming out of the reservoir, and it's going to be, the pressure here is going to be high. So now, and the pressure on this side is going to be fairly high too. So without that big pressure differential, we can do a much better job of metering, and so we won't have a tendency for things to leak by the pump when we're trying to get a precise metering. And the fact that the two are connected means that I can get the right proportion, and we'll have a stoichiometric mixture arriving at the mixture head. So let's see what this might look like. So here is our design matrix written in terms of partial differentials. And so we shouldn't be concerned that, oh, I don't remember all of my calculus. All you need to do is remember that this term in this matrix is telling us how the flow rate changes with respect to changes in the, what was W? The pump speed. And so now all we need to do, and we don't actually need to be able to evaluate these precisely, all we need to do is tell whether or not it's a 0 or a 1. So what are we looking at here, for example? That means these are all x's. That means all three of our DPs have the possibility of influencing the metering. And what's taking care of the metering is the gear ratio between the two pumps. So as I adjust, as I'm adjusting the pump speed here for the high pressure pump, I'm going to change the flow rate, the mixing, and the metering. And as I adjust the diameter, I'm going to just change the mixing and the metering. And as I adjust the gear pump, I change only the metering. So in this case, these interactions may be taking my FRs out of tolerance. First FR2 and then FR3. But in this case, this DP can bring them back into tolerance because it does not influence FR1 or FR2, which in this case is the flow rate and the mixing. All right, so here we go. We have a kind of summary here. And so these are undesirable. This makes this a coupled matrix, but when we put it in this way, it is now decoupled because it is a lower triangular matrix, and that is manageable. All right, let's. All right, so there's some text to what I was just saying, and how the DPs, DP1 and DP2, are changing more than one FR. All right, so here's something we can know right away. The matrices must be square. In other words, the number of FRs has to equal the number of DPs for this to work right. So, so here are your choices. If you have more FRs than DPs, then either you need more DPs or you need to reconsider the FRs. If there are more DPs than FRs, the other way around, you won't have a square matrix either, but you'll have DPs, more than one DP that can adjust an FR. So you have a kind of redundant adjustment system. And so what you would do in this case is decide, all right, some DPs we'll use for adjusting and some will hold constant, because we don't need them all adjustable. All right, so now here's a note too. Lots of people, when you ask them, how do you tell if it's a good design, they think, well, fewer parts, make it simpler. And there's a tendency to think that fewer parts will always make a design simpler. Not true. If fewer parts means that we're losing a DP that we needed to have available to adjust an FR, then fewer parts is not better, because we lose independence and we have a design that will not be easy to adjust and will suffer from unintended consequences. All right, so decoupled. A triangular matrix is what we call a decoupled matrix. And they look like this. Now remember and again, don't think, oh no, I have to go back and review my linear algebra book, because I'm going to show you a relatively easy way to do this. But this kind of problem comes up in linear algebra, what equations do I have? So this really represents a series of equations. And because these two things are 0, then FR1 is just a function of this, this element of the design matrix and dP1. So this shows in a series of equations that when I have a triangular matrix, FR3 is a function of all of these things. And so in the order of adjustment, I've done something to dP1, that's changed FR3, then I've done something else to dP2, that's changed FR3 again. Who knows if it's going to be within tolerance or not? It doesn't matter, because now I can adjust dP3, and A33 will tell me how that's going, dP3 is going to influence FR3 and bring that back into tolerance, despite the fact that dP1 and dP2 may have taken it away from where it needed to be. All right, so the best kind of matrix is a triangular matrix. So let's take a look at what's going on here. So if we generalize on this, we can say, all right, someplace out of the matrix I get to dPi and FRI. And the point here is that while dPi is intended to do this influence, we should try to choose it so that this is a 0. So our intent as designers is to try to make the matrix diagonal. So the nice thing about a diagonal matrix, as you may have figured out, is it doesn't matter in which order I adjust the DPs. I can use any order I want, and I won't have to iterate in order to try to get a solution. So what do we do when dP2 influences FR1? So if I had a situation like this and tried to do the adjustment in the order 1, 2, 3, I adjust dP1 to get FR2 where I want it. So, okay, good. Or FR1, rather, where I want it. Now I do dP2, thinking I'm going to get FR2 where I want it, and uh-oh, I've changed FR1 because there's an influence here as well, and now FR1 might be out of tolerance. So, so then I would have to go back and say, all right, I did this first, then I did this second. Now my third step would be here to get FR1 back, and then 4. So I would have 4 adjustments if I try to do the order dP1, dP2, dP3. And what I can do is, the best thing would be find another dP2 that doesn't influence FR1. That might be a better solution. All right. Now, I'm sorry, let me go back here too and just say quickly, if I used a different order of adjustment, if I did, well, you can probably see this, if I do dP2 first, that influences FR1 and FR2, then I'll use DP1 second. So my best order of adjustment, and we're going to work on this order of adjustment, would be 1, 2, 3. All right, and let's see how we can do that systematically. Okay, but so these matrix elements, and the ij tells me where it falls in the matrix. And these are the functions that transform FR, or the DP, into the FR. So if DPI does not influence FRJ, so this we could put an I and a J here the way I'm doing this, right? And then IAJ equals 0, and we do, as I said, we do not need to know exactly how this influence happens, although it could be useful. But in order to figure out the order of adjustment, this is all we need to know. Is it 0 or is it not? Is there an influence there or isn't there? All right, so uncoupled, diagonal, this is the best. And so the only non-zero elements are down the diagonal. So any order of adjustment works. In this case, a full triangular matrix, there is only one order of adjustment that works, and that's dp1, dp2, dp3, and we can see that clearly. Now, if we didn't know that, if we didn't already have this range in a triangular fashion, if dp1 through 6 weren't conveniently numbered for us in the right order, then we would have trouble adjusting this. So let's take a look at this problem. And sometimes you're working with an existing design. So somebody's gone through and done this, and you've tried to work out, let's see, what are the FRs here that we think are important? And then what are the DPs that exist in this design for us to use? And so we've got, so we'll go through and say, all right, what's DP1 influencing? And you go, all right, it's influencing all these things. What's DP2 influencing? Oh, it's just influencing that one. What's DP3 influencing? Oh, we have that. And so you start filling in the X's and O's. Now this one, and I apologize for the wobbly stuff there. This is when you copy slides from one file to another. You're never sure what's going to happen. But these are intended to all line up, obviously. All right, so in this case, we have all 0 elements up here. So this is a decoupled matrix. So what this is telling us down here in the lower part is that we have some unwanted influences. And so, I didn't quite draw that right. Let me have another shot at that. There we go. There's the lower part of the matrix, and that shows the unwanted influences are, and here are the desired influences. Okay. So one of the things we might do is say, is there some other way we can, is there another DP4, 3, or 1 that can avoid these? But at least we know how to live with them. All right. So how do we know if we put an X or an O in? Sometimes there's a scientific relationship. We know that F equals MA, and we can say, all right, we've got how is the force going to change with the mass, and we can figure out what's the acceleration required, and then, all right, so we can figure out what the relationship is. Lots of times we don't know, and lots of times we're putting things in as FRs that almost seem to be unmeasurable. So then we have to think about how do we build a relationship. Sometimes we're putting stuff in, and it's fairly simple. We can look at the thing and say, or sort of write down a relationship. And then maybe all we have to do is say, well, let's see, what different things might be working here, and let's see what makes sense. Sometimes you ask everybody in the room who's working on the project, and if you can arrive at a consensus, then that may be good enough. And actually, consensus building is often a part of design work. When you can have all of the stakeholders in the design agree that yeah, you have the matrix right, then that's enough to move forward. And although that's not always a sufficient condition, that often is a necessary condition to move forward. All right, the other thing is design and experiment. So DOE is actually a very good tool here to use. All right, so this is what I was saying about the tolerances. So, you know, if we have a small roof rack, maybe we're still in that MPG and we're all set. But if it's maximize the gas mileage, well, we have to decide, you know, how much of a change is important. And so we have to decide we need tolerances on the FRs. So it depends on the tolerance and the sensitivity. So this is something, you know, what is the market looking for in that? And that you need to determine. All right, so, so what would be good to do now is, and this shouldn't take too long, so take a look at the shaft and check axiom 1. So there's a matrix function that you can see up in the upper bar, a little thing that looks like a matrix. If you click on that, your Claro screen should go from the list to the matrix, and you can go back and forth. So then get some practice putting in X's and O's in your matrix elements. Now the hope is that you've got at least 2 FRs and DPs in your decomposition of the shaft. There will be some reading up on the web, and you can see some of my thoughts on this kind of shaft design. And so you may need to go there. But your thoughts don't have to agree with mine on the shaft design, and designs can differ, of course, and it'll be interesting to see what you come up with. All right, so here are the rules from linear algebra, and this is going to be just about the extent of the linear algebra that you'll need to know, besides I wrote down, all right, the matrix equations stand for a series of equations that we could write. All right, so how do we rearrange the matrix to get it from whatever it might be to a triangular? So if we change the DP order, we move the corresponding column, and if we change the FR order, we move the row. So DPs take columns with them, FRs take rows with them. All right, so if we take a look at this matrix, it may not be immediately obvious to everybody that this could be a decoupled matrix. Obviously, it's not uncoupled because we have off-diagonal terms. And obviously, we're going to have some problems because we're going to go, geez, how do we do DP3? Because I get over here. All right, so the order of adjustment 1, 2, 3 is not going to work. So let's see how we can do this. Now, we're looking at a 3 by 3 matrix, but of course, this could be a 30 by 30 matrix, in which case I really want a computer to do it. 3 by 3 you can almost do by trial and error inspection. So, all right, so the first thing now is that we're going to move the columns. Now, this can be easier if we write the DPs across the top. So now we've got DP2 here, DP1 here, and DP3 here, whereas up here we had DP1, DP2, and DP3. So now instead of 1, 2, 3, it's 2, 1, 3. All right, so this is looking a little bit better. And so I'm going to start off, this would tell me I start off with DP2, but let's see what happens. So this still isn't a lower triangular. All right, so here's where we were a moment ago. So, so now what do we have? Well, we still have DP2, 1, 3, just like we had before, but now we've shifted 2 of the rows. So we've taken this row and moved it up here, and then shifted these 2 down. So now the FRs are 3, 1, 2. So again, we've got dp2, dp1, and dp3 on top of the columns. So if we write the equations down, we haven't changed the equations. We still have the same set of equations. But what we have now is a lower triangular matrix and a clear order of adjustment, 2, 1, 3. And I'm doing first dp2 to get fr3 where I want it. That's going to change 1 and 2 perhaps in some unwanted way. Then I do dp1 to get fr1 where I want it. And that's not going to do anything to dp3, note. And then dp3 to get fr2 where I want it. So here's a question. Is there another order of adjustment that can also be used? So that's what we were just saying in the previous slide. So this is decoupled. Now, the interesting thing about this is going back to the way it was presented, and so this might be an existing design, or this might be a design that you come up with. And had you tried to adjust this in the 1, 2, 3 order, you would be taking FR1 out of tolerance when you did dp2, because that element, dp1, that element is non-zero. So that would be taking FR1 out of tolerance. And if you thought you were doing dp2 to get fr2, then you do dp3, whoops, and you will take fr2 out of tolerance. So you're going to be iterating, and you go, oh no, I've got to fix fr1, so you go back to dp1, and then you go, oh no, I've taken dp2 out of tolerance, or fr2 out of tolerance, so you go back to dp2, you try to get that back in tolerance because you've taken it out of tolerance with fr3, which did nothing to with dp3, which did nothing to fr3. All right, so you end up in an iteration situation. Now, the thing about this is let's see, what am I doing? That's imaginary complexity. It seems like a complex system. I keep fussing around with the order of the DPs, and adjusting this DP going back, it seems complicated. But once I know the order of adjustment, it's not complicated. And note that I could actually switch these two and it wouldn't matter, because I can put this thing back into a triangular form. And so if I switch those two and these two both, it still is a triangular matrix. So, and I'm still adjusting dp3 to fix fr2 and dp1 to fix fr1, but because they're only influencing one other, or they're only influencing each of them one fr, then I won't have to iterate. So as long as I do dp2 first, this one is first. That's an awful first. As long as I do dp1 first, I'm all set. I can do then 1 and 3 or 3 and 1. Doesn't matter. All right, so here, what is the order of adjustment? Now, we've been using lower triangular. This is an upper triangular matrix. And so you may be more comfortable shuffling it so it looks like a lower triangular matrix. Or you might just look at it and say, I get it. Because up here I have got dp3, dp2, and dp1. And then with a little inspection, we can quickly see, I get it. dp3 is going to influence all three of these. I got to do that one first. And I'm going to save the one that's going to do just one fr for last. So, that shouldn't be too tough. Now, here's an interesting thing. So far, what have we been doing? We've been trying to advance design by playing around with symbols and largely words. We're doing a decomposition. We're calling things certain things. We're trying to figure out, all right, is it collectively exhaustive, mutually exclusive? And people might say, I thought engineering was equations and drawings and blueprints. And what are we doing mucking around with all of this? Well, what we're trying to do as engineers is create value by thinking. And if we look at this book by Baum called What is Thought? Very interesting book. Right in the beginning, he says, thinking is all about semantics. Now, Baum is worried about, can we really create intelligent computers? And if we do, then we have to decide what thinking is. And so he comes up with it's all about semantics. Well, what is semantics? So semantics, all right, we'll get back to that. All right, but what we have done in our process now is we have taken the design problem and reduced it to symbols. Where else have we done this kind of thing? In our analysis. We take a problem and we turn it into mathematical equations, which are symbols. We manipulate those symbols according to certain rules, and we come up with a solution. So, so the semantics, we have symbols, and then we manipulate those, and then we have a better design. The quality of the design has been improved because right here, the order of the adjustment of DPs becomes obvious. Order of adjustment. So what you can do is you could put some matrices in, you just make something up, or you could work on a problem, and you'll find that there is a reorder function in Eclairo, so you can adjust matrices. So you might want to play with that. All right, before we leave this, and that is the main message actually for today. But two of the things that people stumble on when they're trying to do this kind of work, one, they don't start from a good decomposition, so they haven't got a decomposition that's collectively exhaustive and mutually exclusive. So if you're having trouble implementing this, go back and check that. Another thing is that they can't figure out what the equation should be or what could I measure to see if I've got the FR. Well, we'll talk more about measurement in a subsequent lecture. But remember for right now what Lord Kelvin said. If you can't measure it, you can't discuss it. If you can't put a number on something, you can't discuss it. So whatever it is you're trying to do, you should be able to put a measure on. Now the next thing that happens is, and the next thing that people frequently stumble on, is they end up with these fully coupled full matrix. It's what I call a box situation. Maybe not in the entire matrix, but just enough to keep you from having an adjustable matrix. Not all matrices are adjustable. So sometimes it seems that subsystems appear to be influencing each other. And so we have this kind of situation where we have we're looking at it. We could just do these 2 by 2. This could be a much bigger matrix, but we're just going to look at a 2 by 2 situation. Because anytime we have a 2 by 2 situation, we might extract from the matrix, and if we have all x's here, then we are not going to be able to pull this into a diagonal matrix. And so if we're designing a system from the beginning, we have this opportunity to do something here. So lots of times when we're starting from the beginning, we will just stick an O in here, and that will be putting this 0 is an expression of our optimism, essentially, that we will be able to find design parameters that do that. So if, as I'm doing the decomposition at each level, I'm going to make a matrix and check it, I find out that I should not have put an X there. How can I figure out how to do this? Well, how do you know when to do that and how to prioritize? So I can get into this and have a non-value iteration, a non-value adding iteration. So here's how you stay out of this trap. First of all, here's how you get into it. So DPA, all right, so A is supplying something of value to the customer. In order to get A, I need B. And B supplies some secondary value. So, so I've named the matrix elements AA, AB, all right, so forth. You can see that. Now, because A is supplying a primary value and B is only a secondary value, then A should dominate. So the question is, when I arrive at something, and if these are all non-zero, I got to choose one to make zero. Which one do I choose to make zero? This one or this one? Should that be a zero or should that be a zero? And what we need to do is take a look and say, where is the primary value? What is the most important thing? If I took that thing away, I would have a worthless product, and it might be the most difficult thing to supply. So let's say I'm Henry Ford, and I have to choose between a motor and brakes. Now, they both influence speed. Yeah, they could influence each other. Which is going to dominate? Well, I could have the greatest brakes in the world, but if I don't have a motor, the car's not going anyplace. So I ought to say, all right, I'm going to give priority to solving the motor problem, and then I'm going to figure out the brake thing so that it doesn't mess up the motor. So this is what we're striving for. Let's see what's primary, and let's see what's secondary. All right, here's another example, lobster boat. So FR1, provide seaworthiness. I want the boat to float. FR2, catch lobsters. So here is a boat operating, and I don't know if any of you have had the pleasure to do this, but the lobster traps need to be on the bottom of the ocean, and you got to pull them up with a rope, and sometimes they're difficult to get up. So here's a little winch that's pulling the lobster traps up, and here they are, and you pull the lobsters out, and put them behind you, and you clean them up, and you get ready to put them and put bait in them, and you get ready to throw them overboard again. Now, when I'm pulling here, there's a lot of tension. There can be a lot of tension in this rope, and you can see sometimes it breaks. Here's a little splice. All right, but here's the problem. Look at how the boat is tipping compared to the horizon. So this load here is, in pulling up the lobster traps, does have an influence on the seaworthiness, because if this rail goes underwater, everybody's going swimming in the Gulf of the St. Lawrence, and it is cold. All right, so what is the most important? The most important thing is make sure that that the boat gets home, right? We don't let the lobsters get the boat. You want to get the lobsters in the boat, not the boat in the lobsters. So the DP for catching lobsters better not interfere with the seaworthiness. So that means select a 0 for this element, because DP2 is catching lobsters, and this is seaworthiness. There's the FR for seaworthiness, and there's the DP for catching lobsters. So if I don't have seaworthiness, I'm not going to go fishing. So, all right. So what do we learn from the design matrix? Well, one thing is, when we're actually doing the design, what gets designed first? And in general, then when we're using the design, the adjustment that should be of DPs to satisfy FRs without iteration. So this avoids what's called imaginary complexity. And we want to avoid that. So this is what we do with the order of events. There it is. Avoid imaginary complexity. Avoid unintended consequences. Avoid non-value adding iterations. So all of these things, the imaginary complexity, unintended consequences, both take time and value away from the design. So if I can avoid these things, I have a much better design. So save time, reduce costs. And you can take a look at existing designs and do cost reduction by taking out the coupling and avoiding the imaginary complexity. All right, some of the things from the previous lecture, lists and themes can help with the decomposition, but they cannot replace intelligence. You need to think about how this applies. And we can use prioritization to escape coupling. So this is kind of what I'm talking about. The intelligence tells us if I can't get the boat back again, it doesn't matter how many lobsters I caught. If the boat sinks, the number of lobsters caught doesn't matter anymore. So that's where the intelligence comes in. All right, so here's a self-test you can do. There are now several of these matrices, and you can go through and do the order of adjustment. Now, in this case, it's already a lower triangular, and the question is, what are all of the possible orders of adjustment that could avoid iteration? So 1, 2, 3 is not the only one that works. We just looked at a problem like that. So there's a few here that you can go through and take a look at. You can do these either by trial and error. You can do the arrangement thing, because there's only 3 FRs and DPs. It doesn't take you long to try all of the orders to see what works. But you've got to take a look to make sure that you can, you're not taking something out of tolerance or might be taking something out of tolerance with a DP. Anyway, so there's several of those. All right, so you can give that a try, or you can put those into a Claro and give it a try there. Great. Thank you very much for your attention.